My plan is to go through the 52 to 62 evens homework from last time. So, if I take a look at number 52, the first thing you should do is take out a tangent. Now that this is in factored form, you can apply the zero product property to break it into two problems. Then we can do tan inverse to both sides. We can add 1 and divide by the square root of 2 and do cosine inverse to both sides. I recognize that both tan 0 and cosine of 1 over the square root of 2 are unit circle values. So if I go to the unit circle, I notice that tangent is equal to 0 when y is 0. So that happens at 0 and 180. But since they were asking for things on the interval from 0 to 2 pi, yes, we should give that answer in radians. Can I help you? Okay. There's a tablet sitting here. Do you suppose it's this? Okay. Double check the login to make sure it's yours before you steal it. Good. See you later. I also noticed that cosine of 1 over the square root of 2 is a unit circle value. And you might say, no, it's not. Remember that 1 over the square root of 2 is the same thing as square root of 2 over 2, which is certainly a unit circle value. And that is at pi over 4, as well as 7 pi over 4. So these are our answers, but keep in mind we should do one other thing because we have a tangent in this problem. We should check to make sure that where tangent is undefined isn't one of our other solutions. So remember, tangent is undefined at pi over 2 and 3 pi over 2, and neither of those are answers anywhere else, so these 4 answers are fine. There's nothing we need to throw out. 54 is the next one. So here we have sine x times tangent squared is equal to sine x. First thing I would do here is to move everything onto one side. And at that point I notice that, hey, I have a sine x in common with each term. So I can factor that off. And then I can apply the zero product property. So when I take sine inverse to both sides, I notice that 0 is a unit circle value. Sine is equal to 0 at 0 and pi, just like before. If I try to get tangent by itself, I'd add 1 to both sides and then square root both sides. Since I have a plus or minus, I have to break this into 2 equations. So tan inverse of 1 happens at pi over 4 and also at 5 pi over 4. Tan of negative 1 happens at 3 pi over 4 and 5 pi over 4. But again, remember, since we have tangents here, we also have to worry about when tangent is undefined. That happens at pi over 2 and 3 pi over 2. But those aren't answers anywhere else, so we don't have to worry about it. These 6 are our solutions. (56) 2 sine squared x is equal to 1. So here, notice that there's just one single trig function in this. So I can just try to get that trig function by itself directly. I don't have to do any factoring. So I'll divide both sides by 2, and then I'll square root both sides. Remember what happens when I square root both sides of something? Yeah, I get that plus or minus. I don't know why I'm not writing this in red, though. Oops-a-daisies. Yes, Gabby? Yep, everything in those blue boxes. So if I do sine inverse of both sides, I have to break this into 2, right? So the square root of 1 is 1. And remember that 1 over the square root of 2 is the same thing as square root of 2 over 2. Right, we just addressed that a moment ago. And I notice both of those are unit circle values. So this happens at pi over 4 and 3 pi over 4. This happens at 5 pi over 4 and 7 pi over 4. And those are my answers there. (58) I notice that I have a sine squared and a sine on there. So I figure that this one's going to have to be done kind of like a quadratic factoring. And if I pretend that sine x is equal to y, I have exactly a quadratic, right? So one way I can solve a quadratic is via factoring. To factor a quadratic like this, I have to find two numbers that multiply to give me a times c and add to give me b. Hopefully it seems obvious that those two numbers should be 2 and 1. So I can break that into two groups now. I can take a 2y from the first group and a 1 from the second group to give me y plus 1 times 2y plus 1. But remember, we weren't solving for y's, we're solving for sines. So that's sine x plus 1 times 2 sine x plus 1. And then we apply the zero product property, which allows me to break this into two equations. And if I subtract 1 and do the sine inverse, I get sine inverse of -1. That I recognize as a unit circle value. When I go and I look, that is 3 pi over 2 only. Over here, if I subtract 1, divide by 2, and then do the sine inverse, I get sine inverse of -1/2. If I go to my unit circle, that's a unit circle value. I find 7 pi over 6 and also 11 pi over 6. But the directions for this problem were a little bit different. Here it wanted all the solutions. So the way I will write these then is 3 pi over 2 plus 2 pi k. Yes. Oh, okay. You're good, though? Okay. So there are all the solutions. Again, to find all the solutions, all you need are the solutions between 0 and 360, and then you tack on a 2 pi k or 360k at the end of them. And that ought to do ya. And then we have 2 more, I think. Is that correct? Yeah, I think so. So we have 60. 3 sine. I'm going to replace these t's with x's, just because if I don't do it now, I'm going to end up turning it into an x halfway through, and then problems. I said problems. That's all. Okay. So, I will start by observing that I probably want to subtract the 2 cosine squared over. But if I do that, there's no factoring I can do as this is currently written. Do you guys all observe that? Yeah, which is kind of poopy. So maybe there's an identity or something I can use. Yeah, hopefully you said, well, if I turn cosine squared into 1 minus sine squared, I can at least turn it all into the same trig function. And if I distribute that negative 2, I have positive 2 sine squared plus 3 sine x minus 1 equal to 0. No to do what? No, all I did was I took the negative 2 and I distributed it through, oh, that should be a negative 2 there, huh? Is that what's confusing? Okay, so we'll pretend I don't, right? So that's okay. We can think about it this way, right? That's probably the way you wrote it at first. Is that right, Julia? Okay. And then, well, I see something with sines and sine squareds. So we'll pretend that sine is y. And probably if I'm going to factor this, I'd want to write it in standard form, right? You agree with that? Oops. Squared. And that's what I had done, is I just wrote it in standard form with the y's there. But whenever you do that, it's fine. So to factor this, I need to find 2 things that multiply to give me negative 4 and add to give me 3. Hopefully you'd say that's 4 and negative 1. So I'd have, 2y squared plus 4y plus negative 1y minus 2 equal to 0. I take a 2y out, and I take a negative 1 out, and then I have y plus 2 times 2y minus 1 equal to 0. And then I put my signs back in, because remember, we're not solving for y, we're solving for sine x. Or solving for x, excuse me. Hi, Mr. Cater. She is absent. You're welcome. If we then apply the zero product property, notice how quickly Mr. Cater left when I started talking about math. We can break this into two equations. To solve the first equation, I'll subtract 2 and then do the sine inverse of both sides. If I do that, though, and type in sine inverse of -2 into my calculator, what am I going to get? An error. This thing gives you no solution. You remember you can't do the sine or cosine inverse of values that are bigger than 1 or smaller than -1. This one, however, we don't have any problem. If we add 1 over, divide by 2, and then take the sine inverse of both sides, we have sine of 1/2. That's a unit circle value. If I go to my unit circle, I see that that happens at pi over 6 and also at 5 pi over 6. Oops. But they didn't ask me for the answers just between 0 and 360. They wanted all the solutions. So all I have to do is tack a 2 pi k on the end of those. Gabby? Why? Okay. Do you need to go get a drink, my man?
I need a water. Can I try to get one?
Yeah. I thought I saw an unclaimed case of waters on that table in the B-wing triangle. You could probably just steal one of those. Maybe leave a quarter for their effort. Okay. Or you just go to the vending machine or something. He seemed like he was suffering. I know how it was. The first month of the school year, I was coughing the whole time. It was miserable. No, just sick, like an unshakable cold. Yeah, I don't got allergies, which is nice. But apparently, I did have an invincible cold. It wasn't invincible. I eventually defeated it, but it took a long time. All right, I think the last one here is 62, right? Yeah, I thought so. Okay. First step should be 2. Yeah, subtract the 2 over. And you'll notice that this looks an awfully lot like a quadratic equation. Yeah, and you'll notice that it is remarkably similar to the problem before, right? Where we had, not that, whoa, too far. Didn't we have this before? No, we had something similar to this. We didn't have exactly this one, though, did we? Oh, is it this one? Oh, yeah. Oh, yeah. So, and then using number 60, we get x equals pi over 6 plus 2 pi k, k an integer, and 5 pi over 6 plus 2 pi k, k an integer. Shame on them for not doing a better job editing their textbook, putting 2 of the exact same problem in there. That close together. But how nice if that was a bonus at the end of doing this problem set, where you're like, oh, I'm so tired, there's so many of these, and the last one is exactly like the one you just did, and you're like, yes, yes. Okay. Everybody's asleep. I did a good job today then, huh? what I want to do here for a moment is talk about what the plan is for tomorrow. I am going to be here. But the plan for tomorrow is just to work on the test review. So the test review is this document. I'll have a copy for you tomorrow. If you're like, man, I need to start tonight, I can't wait, I would say take a hard look at your life, number one. And number two, the review is on haiku, so you could start tonight if you absolutely have to. But the kinds of problems that I'm going to ask you to do on the test are going to be to find exact values using the sum or difference identities. And you should be able to write your answer in a fully simplified form. So I gave a couple of examples here of that. You should be able to find the exact value using a half angle identity and write your answers in a fully simplified form there. You should be able to, given a solution to a trigonometric equation, find all the other solutions. So oftentimes drawing a picture is going to help you answer that. And then just some like regular old solving ones where I give you a solving problem and ask you to find the solutions on some given, or for some given set of values of x's. So some of them are in degrees, some of them are in radians. And that's going to basically be the test. So the test would be a similar format, similar number of questions. I would give you the identity sheets as well as a unit circle. So not much to memorize, right? The plan is Tuesday after Thanksgiving. Did you find one? Nice. Any questions about that for me? Okay. In addition, for those of you that are exceptionally nerdy among us, also on haiku I have the key for this with worked out solutions written down on it. We'll go through them in class on Monday. But if you find yourself on like Black Friday going, man, should I go try to get a $200 57-inch television or work on my math homework, and you opt for your math homework, you can check your answers as you go here.